Fusion, the international science radio show.
Hello.
Kim, how are you?
All good.
I'm good.
Good, thanks. How are you?
I'm good, thank
I'm Dr. Kim Reid, and I'm a climate scientist at Monash University with the Centre of Excellence for Climate Extremes.
you. Fantastic. And so, as a climate scientist, what is going on with these weeks and weeks of rain over eastern Sydney, eastern Australia?
Isn't yes. Well, I'm in Melbourne, so it's weird because we've had dry weather for
You've had dry weather,
weeks.
so I didn't
We've had
realise it was
completely
just New
dry.
South Wales. Is it New South Wales and
Yeah,
Queensland?
I think New South Wales and Queensland. Yeah, I had to water my plants the other day because they hadn't been
Wow.
rained on for a few days, for weeks.
Is that common that Victoria misses out?
Um, it I wouldn't say, I don't know. I don't
Hmm.
think it's either common or uncommon. It can be both, but fairly I'm fairly certain we've had a bit of a positive southern annular mode at the moment. So there's a bit to unpack there. You've probably heard of El Nino and La Nina, which is what we call a climate driver. And
Yes.
these are variations in ocean sea surface temperature and winds across the Pacific that can influence Australia's weather. But El Nino and La Nina, which is referred to as ENSO collectively, is just one of many. So in the Indian Ocean, we have the Indian Ocean dipole, which again refers to temperature differences across the Indian Ocean, and that can affect our weather. And to the south, we have what's called the Southern Annular Mode, or SAM. And that refers to the north-south shift of winds that flow from west to east around Antarctica. And that north-south shift affects the type of weather systems that hit southern Australia. So during a positive SAM, we tend to get cold fronts and low pressure systems move south. And places like Melbourne are more likely to be stuck under high pressure, which is what's happened for us in Melbourne. But on top of that, you tend to get more tropical moisture that's able to, I guess, penetrate south. So during a positive SAM, you tend to get wetter conditions over New South Wales and Queensland. So I believe we've had quite a few cut-off lows over New South Wales. So that's when you get a low pressure system that's broken away from the fast winds that was around Antarctica that are kind of like the highway for storms. So they've pulled off the highway and they've got stuck over New South Wales. And so when you've got a low pressure system stuck over New South Wales and this tropical moisture that's able to penetrate further south, you have a recipe for heavy rainfall. And we've had a few of those lately, particularly in April when there was quite heavy rainfall in New South Wales.
And so when you get it for like several weeks in a row and it's not raining itself out, is it because it's refreshing from somewhere else or is there just that much water in the air?
Yeah, so it's not the one system continuously sitting there. It'll be refreshing itself. And just when you have climate drivers in certain phases, like a positive SAM, it just increases the likelihood of that type of weather system occurring.
And so now that we've got the weather chat out of the way, what is the focus of your research these days?
So my main area of expertise is a phenomenon called atmospheric rivers, which is what I did my PhD on. And so these are strong, narrow regions in the atmosphere that have really strong water vapor transport. And they're called rivers because the amount of water vapor flowing through them is about equivalent to the water that flows through the Amazon. So technically, they're the largest freshwater rivers on Earth, but they're not on the ground, they're in the sky, in about the first 1 to 3 kilometers of the atmosphere. And there's usually about 6 or 7 on the globe at any one time, and they're quite common. And they usually bring a lot of beneficial rainfall. So places like California, when they don't get enough atmospheric rivers, that's when they end up being in drought. But on the other hand, you can also get really strong atmospheric rivers that cause immense flooding. So we saw atmospheric rivers during the February 2022 floods in Queensland, where we saw 3 days in a row of 200 millimeters of rain due to an atmospheric river as well as a cutoff low. And so my PhD was about understanding weather systems over Australia because there'd been a lot of work in the Northern Hemisphere, particularly in the west coast of the US. California does a lot of atmospheric river research, but Australia had sort of missed out. And so I thought I would fill that niche. So, yeah, do you have any questions? I could
Yes, yes,
monologue for
yes.
ages.
Sure, sure, because it's really interesting. So a lot of people don't know about these atmospheric rivers, and so are they sort of are they always there? Are they ones that have been there for very long periods of time, or do these sort of come into existence over a very short period of time and then dissipate?
Yeah, so they come and go just like cold fronts or low pressure systems. They sort of move with these synoptic weather systems, and they might last a couple of days or two, a day or two, and they might reappear every week to 10 days. So yeah, sort of similar frequency to a cold front or a low. And there are parts of the world where they are more likely to form. So there's one that has a special name called the Pineapple Express that sort of goes from Hawaii to California, called Pineapple Express because it starts in Hawaii. And so there are parts of the globe where you tend to get more atmospheric rivers, and the west coast of continents is one of them. But Australia and Asia is a bit weird because we get a lot on our east coast as well, which is unusual. So my work on Australian atmospheric rivers has sort of highlighted some of these differences to the traditional knowledge that they know in the Northern Hemisphere. So in Australia, not only do we get some of our most intense ones on the east coast, we also get atmospheric rivers that form closer to the equator. So you might have heard of the Northwest Cloud Band, which is, if you look at a picture of a satellite map on the news, and there'll be a giant band of cloud that stretches from northwest to southeast Australia, and it's like this sash over Australia. And so these sorts of versions of atmospheric rivers haven't been studied as much in the Northern Hemisphere because they're at a higher latitude. So the systems are just slightly different.
So you're focusing on the ones that people haven't paid so much attention to in the past.
Yes, particularly over our part of the world that sometimes gets neglected.
And this one you just described, this band across Australia, is this responsible for some of our rain systems?
Yeah, absolutely. So sometimes you'll see rain in Uluru, and you get waterfalls off Uluru, and that's when you've got a really strong northwest cloud band. And because you have this link between the tropical areas, which are warm and moist, and the extratropical areas, which are cold but unstable, this sort of meeting of two types of air between northern and southern Australia is when we often get really intense rainfall events. So some of the extreme rainfall in spring 2022 in southeast Australia was associated with these big northwest cloud bands.
And has the behaviour of this big cloud band changed with climate change?
So that's one thing we were trying to investigate. I was trying to investigate as part of my master's. Unfortunately, we don't have long enough data sets. So satellites really came into action in about 1979. So you have about 30 or 40 years of data, which, because rainfall is what we call variable, it swings between drought and flood so much. In order to tease out a climate change signal among all the noise, you really need much longer data sets. So we know with climate change that the amount of moisture in the air is likely to increase, and therefore that will increase the moisture in these atmospheric rivers and northwest cloud bands. But what we aren't as confident about, or what there's a lot more uncertainty about, is how the actual weather systems might change. So during a northwest cloud band, you typically have high pressure over Perth and southwest Australia and high pressure over northeast Australia and Queensland. And that sort of forces this convergence of air over the middle of the continent. And when the two air masses meet, that's when you get this, it's like a big front of cloud. And it's the behavior of these weather systems that we're not quite sure about yet. Climate models aren't quite high resolution enough to really capture these patterns. And so we know that the moisture will increase, but exactly when and where and the frequency of these weather systems is a lot more uncertain. But scientists are doing a lot of work to try and understand this. And there's so much development in models lately about creating super high resolution models that are able to capture these weather systems better. So hopefully we'll have more answers in the next few decades.
Mm. So there's so much there. So the atmospheric rivers, are they affected by things like rainforests and deserts being underneath?
Yeah, that's a really good question. So places like the Amazon you often get an atmospheric river off the east coast of South America because you have all that moisture coming off the Amazon. Whereas for something like Australia, you can't get the moisture off the desert. The moisture has to come from the oceans further afield. So you really need these large weather systems, like a strong high pressure system that's sort of forcing moisture over the desert in order to get that rain. And that's why when you do get them, they're quite spectacular to see on a satellite image and to see waterfalls off Uluru because it's not normal over a desert.
It is. It is amazing. I mean, I'm trying to think where we were. I took what's it called? Ah, I can't think of the name of the train. The train that goes
The
from,
Indian Pacific
yes,
or
yes, yes, yes.
the
And we
Ghan.
stopped in the desert to have breakfast and it rained on us.
Oh, wow.
I think Rawlinna was where we stopped.
Okay, well, I don't know what that is.
Oh well, it's a place in the desert, in the middle of the desert.
Okay,
There's a
you weren't
train
expecting
station.
that.
There's nothing else there, and it just rained. So
Wow. Probably
yeah,
didn't have an umbrella on you.
we had to go back in the train.
Oh, wow.
So that's interesting. So how did you come to study this?
Well, okay, so I finished my bachelor degree and I applied for the Bureau's forecasting graduate program. I got rejected, so I thought I'd do an
Ah,
honors just to fill the time. Um, and I ended up getting a scholarship to study Victorian rainfall because I was the only person who applied for the scholarship. So my advice is always apply for scholarships because you might get it by default. Um, and I was doing a review of the literature to just understand causes of rainfall over Victoria and realized that the studies on northwest cloud bands hadn't been updated since the 90s. And this was 2018, 2017. So there's a good 20 years of data that we didn't know what was happening. So I decided I would focus on that for my master's. Ended up loving the research and lost interest in forecasting and decided
ah,
to do research. So I'm kind of glad I got rejected in the end.
hmm.
But so I did my master's on Northwest Cloud Band, which is one specific atmospheric river. And then for my PhD, decided I could broaden it to look at atmospheric rivers generally. And because there hadn't been much work on Australia, I thought strategically, this is a good idea to get into. I can become the expert. And I sort of did. I ended up working on some international projects where I was the only Australian there as a PhD student, which was a little bit intimidating, but it was also really good career-wise to become, the expert on something so early on. But now I'm a postdoc now, so about 2 years post PhD, and I'm trying to. You don't just want to get backed into a corner where you only research one thing. So while I do love doing atmospheric rivers, I also try to look at rainfall more broadly these days.
But you're still sometimes looking into prediction based on the atmospheric rivers?
Yeah, so there are some really cool studies out of Europe a few years ago where basically they looked at so in short, rainfall is really hard to forecast. Um, because it's just very messy, it's very complex, and models often aren't high enough resolution to capture all the fine scale physical processes that occur. So there was a study out of Europe where they looked at the water vapor transport, which is what you use to define an atmospheric river. So how much moisture is flowing over the atmosphere. And they showed that if you use the water vapor transport to forecast extreme rainfall, instead of the actual rainfall, you can improve the forecast lead time, so how much warning you have, by a couple of days. And I thought that was really cool and decided to apply it to sub-seasonal. So this is multi-week forecasts, or long-range forecasts that you might see the Bureau issuing. Now, you can't predict a weather system more than 7 or 10 days ahead. So you can't predict that there's going to be a cold front over Perth in 10 days, but you can predict whether there's an increased or decreased likelihood of rainfall. So I collaborated with the Bureau of Meteorology using their long-range forecasting model to see if we, instead of looking at rainfall in the model, let's look at water vapor transport and say if the water vapor transport exceeds some kind of threshold, let's say it rains, and we'll use that as our rainfall forecast. And then I compared that to actual forecasts for about 30 or 40 years and found that in some places, the forecast is more accurate if you just look at whether there's high water vapor than if you look at the actual rainfall in the models. So there's always a lot of work in trying to improve forecasts, and a lot of it relies on the technology. So having powerful enough computers to be able to run really high definition models. And that takes decades to improve. But things like using other variables, you can, I guess, squeeze out more accuracy without having to wait for these technological advances. So the idea was, well, maybe we could use this water vapor transport as a bit of a proxy, an indication of rain. And they're doing this in the US now. It's called, there's a program called Forecast Informed Reservoir Operations, or FIRE, where they're working with dam managers in California and using the forecasts of water vapor transport to indicate whether there's a strong atmospheric river about to hit California and whether dam managers should therefore release water to reduce flooding. So we're not quite at that level yet in Australia, but there's some really cool precedents overseas that I think would be cool to implement here.
And one of your papers got some media attention a few years ago.
Yes, a few of them do. Well, so you may remember in March 2021, there was heavy rainfall and flooding in Sydney. And this was during my PhD, and it was associated with atmospheric rivers. So we thought it would be cool to see how often these sorts of events might happen in the future. So we teamed up with some folks in the US who helped run some models for us to look at the likelihood of similar scale events happening in the future. And we found that events like the March 2021 event are projected to be about 80% more frequent by the end of the century under both high and moderate emission scenarios. So that was 2021. Then 2022 happened, which you might remember was record highest amount of rainfall on record for Sydney, massive flooding everywhere. And so it was a little frustrating because we'd just done this study on 2021, and then had we waited a few months, we would have had this even better case study. But on the plus side, it meant that when 2022 happened, we had this research that we could talk about with the media. And that sort of, I guess, was my first real big media experience and propelled me into journalist phone books, I guess. So we went, yeah, as a PhD student, I was doing live media interviews, which is terrifying, but a whole lot of fun. And I think that's really helped spark my interest in doing science communication. I really enjoy explaining the weather to non-technical audiences. And nowadays I do a lot of media.
That's great. And so how did you come to the comedy schools to learn stand-up?
That was a random post I saw on LinkedIn, and I thought, that looks fun. I'm going to click it and sign up. And I didn't think I'd get in, but I did. And so it's a relatively new program where David, who runs it, is training scientists to do comedy. Yes. And the idea is to present your research as a stand-up routine. And it's supposed to be about 80% science, 20% comedy, but really I think it's more 50-50. So a bunch of scientists, about 23 of us, I think, for Melbourne. We had about 2 months of training where we learned how to craft narratives, so how to present our science in a nice, interesting way. And then we learnt about the theory of jokes, which was super interesting. So what makes a good joke and what doesn't make a good joke. And we weren't allowed to use dad jokes or puns. And the logic behind that is because when you tell a joke, if the audience has to think about it a little bit, it's more rewarding. They get like more of a dopamine rush if they have to think about it just a little bit to get the joke. So if the joke is too obvious, like a dad joke or a silly pun, or if someone explains a joke to you, it's no longer funny because you didn't have to work for the laugh, which I found super fascinating. So learning the psychology of jokes was really cool. And the theory of how to write a joke. You've got to have your setup and then your punchline. And of course, I was watching a lot of stand-ups after that to try and watch them. And I was watching Carl Barron, who comes across as funny, silly, and you'd be surprised how methodical his jokes actually are. There's actually a lot of theory behind his jokes, even though he comes across as a bit carefree and like you don't know how much thought he's put into it. He's obviously put a lot of thought into planning his jokes, and that's why he's very successful. And then we just practiced and wrote our scripts, and we had a one-on-one meeting with a comedian, so Seaton, who was on, I believe he was on Australia's Got Talent, who helped workshop our jokes, which was really, really good. He added a few in that were very funny. And then just practice and practice. And it was such a fun experience to be a part of this cohort of other scientists who were in different fields to me, but still similar career levels, and hearing everyone's jokes. And then we performed at the Melbourne Comedy Festival in front of an audience of about 100, which at first was terrifying, but it was actually so much fun. And it was an absolute blast.
Fantastic. And did you do one performance or did you do a few?
So I just did one, but I've heard of other people in other states who've done the program and they've been asked to do their talks numerous times. So we'll see.
And would you do something like that again?
Oh, absolutely. I had a lot of fun. It was a lot of work, like a 10-minute comedy skit. Took quite a few hours of work and then preparing it so that we could get our timing perfectly, because it's all about timing. It was a lot of work, but it was so much fun.
And did you have to cut out some bits of the science to make room for the jokes to fit the time?
Yeah, it was really hard at first to figure out where to start, because talk about your research in 10 minutes and you're like, well, I got to explain, 3 years worth of climate science in 10 minutes. But I guess so at the start, I found I was trying to talk about too many things, but I decided then to just focus on one or two results. So I focused on the forecasting result that I spoke about earlier and the climate change paper that got a lot of media attention, and just focusing on a couple really helped to keep the science simple so I could then put most of my effort into making it engaging, because that was what we were trying to do.
Would you introduce that into your lectures or any of that sort of thing?
Definitely. I think students would love that. I mean, scientists are not known for being engaging, especially in lectures. And I know as an undergrad, I found sitting through lectures quite challenging. And just learning how to keep people engaged by peppering jokes throughout is absolutely a useful skill.
But extra work.
Yes, harder, but it's rewarding, I think.
And then you get to reuse the jokes the next year.
Oh, absolutely. Hopefully they don't tell each other.
Is there anything I haven't asked you you'd like to talk about?
No, I can't think of anything.
Would you like a concluding statement?
Sure. Oh gosh. I guess my main conclusion is that there's a lot of great people doing a lot of great work trying to understand rainfall, climate change, forecasting, and it's tricky, but we're doing our best. And I know climate scientists especially get a lot of criticism externally, but most climate scientists I know are brilliant. scientists and awesome people.
Great. Well, Kim, thank you so much.
Thanks for having me.
Study science, because you will find in the study of science a richer, more rewarding life.